Okay, so today in this video we're going to look at simplifying radical expressions. Some prerequisite information you need before you watch is make sure you know your perfect squares, cubes, and quartics. The square root of 100 is 10, the cube root of 27 is 3, the fourth root of 16 is 2, and so forth. Also make sure you know how to simplify non-perfect radicals with exact answers. Two examples of this would be the square root of 8 and the cube root of 32. Obviously 8 is not a perfect square. So the way we have taught you to simplify the square root of 8 is you want to split 8 up into two factors that multiply to give you 8, one of which being the biggest perfect square that divides into 8 evenly. And that will obviously be 4. And you multiply 4 by 2 to get 8. Well, the square root of 4 is 2, and the square root of 2 can no longer be simplified, so the square root of 8 can be rewritten as 2 root 2 or 2 square roots of 2. The same thing can be applied to a cube root. So since 32 is not a perfect cube, we're going to simplify 32 up into two factors. Okay, and so the largest perfect cube that would give you 32, or that goes into 32 evenly, is 8, and 8 needs to be multiplied by 4 to give you 32. Since 8 is a perfect cube, the cube root of 8 is 2. The cube root of 4 can no longer be simplified, so your answer here would be 2 cube root of 4. These are called exact answers. We're going to apply this into the video today, except we're going to be looking with variables instead of with numbers. Before we start some examples, just a couple vocabulary words. The big square root or cube root symbol, as you saw in the previous slide, is actually called a radical. The reason we don't want to say square root or cube root is because it could change. It could be a fourth root, it could be a fifth root. The number underneath the radical is called a radicand. And the where this n up here, this is called the index. Okay, so if we're working with a cube root, the index is a 3. If we're working with a fourth root, the index is a 4. And you can keep going up to fifth roots, sixth roots, whatever you want to do, as high up as you want to go. Now, when you guys have worked with square roots this year, there is no number that shows up here. Just make sure we know that when we're working with square roots, it's assumed that it's a 2. Okay, we don't take first roots of numbers, so that's why we don't write the 2 down when we're working with square roots. Alright, so we're going to start off with a really easy example, the square root of y squared. We should all know that the square root of y squared is just y. The reason is y squared is equal to y times y. And the definition of a square root is what number times itself will give you that number. Keep this in mind as we go through the examples today. So it gets a little bit more complex when you're working with the square root of y cubed. Y cubed is not going to be a perfect square. Okay, so we're going to think of this similar to what we did with the square root of 8. We are going to split y cubed up into two numbers that multiply to give us y cubed, one being a perfect square. Well, in the previous example, we saw that y squared is a perfect square. So what do we need to multiply y squared to get y cubed? Just y. Y squared times y will give you y cubed. So we already saw that the square root of y squared is y. And if you take the square root of y, that will no longer simplify. So your final answer is y square root of y. Okay? And then once again, the reason that this right here, the square root of y, cannot simplify, there is no value times itself that will give you y. Okay, and we're trying to work without fractional exponents right now. We're just working with nice y's, y squareds, variables like that. The same thing applies to cube roots. Looking at this example, we should all know that the cube root of y cubed is just y. The reason is y cubed is defined as y times y times y, and the definition of a cube root is what times itself 3 times will give me that number. So we can say that y cubed is actually a perfect cube. Okay, so let's look at an example that's not a perfect cube. The cube root of y to the 8th power. So we're going to do this very similar to what we did with the cube root of 32. We are going to simplify this into as many perfect cubes as we can. And I'm going to go back to the example that we saw that y cubed is a perfect cube. Okay? We all agree from the previous example. Well, I can write down the cube root of y cubed again. And if we put these two together, remember you add your exponents when you multiply, That gives me y to the 6, which means I have 2 exponents left, so I can write the cube root of y to the 8th as the product of these 3 cube roots, y cubed, and y squared. And since both of these are perfect cubes, they are both going to simplify to y, and you can't take the cube root of y squared, so we're just going to leave that underneath the radical symbol. And to simplify the answer even farther, y times y is y squared, and the cube root of y squared can't be simplified. So this is how we would leave our answer. Notice how I left a little bit of a space between these terms. You really want to make sure you do that so this exponent doesn't look like it's attached to the index. Okay. Now we just did a lot of work for such an easy problem, so some of you guys are probably starting to see a shortcut. Okay, and one of the shortcuts you can look at is working with the index and the exponent. So that way we can kind of skip all this stuff in the middle. One way you can look at it is, how many times does my index divide evenly into my exponent? Well, 3 goes into 8 evenly twice, which is where we get y squared. And with 3 going evenly into 8 twice, that leaves us with a remainder of 2. That is how many y's we had as a remainder. So a really quick way to do these problems is just divide the index into your exponent, and then you can skip all this middle stuff here. So let's look at an example where we have a coefficient in 2 different variables. And we're going to do this one using the shortcut. And typically we don't have to write this down, but since we're talking about that shortcut with indexes, since we're talking about a square root, I'm going to write my index of 2 in here. Okay? So we should already know, based on the prerequisite knowledge, that 4 is a perfect square. So we know that the square root of 4 is 2. Okay? Now let's go ahead and do the shortcut. 2 goes into 5 evenly twice with a remainder of 1, which means we're going to have 1x left inside the square root symbol. For the y's, 2 goes into 4 evenly twice with no remainder, which means we have no y's left over. Now, we don't want to leave our final answer like this. The proper way to leave your final answer in these situations is your coefficients first, then your variables that are simplified outside of the radical in alphabetical order, and lastly, you want to write whatever's left inside the radical. So this right here, 2x squared y squared root x, is the simplified version of the original problem. Okay, now we could have done this the long way, and we could have split all of this up and written everything out, and you'd get the same answer, but by using the index as a shortcut, you're really going to save yourself a lot of time and a lot of work. Okay, so we're going to look at one last example, and this time we're going to look at a cube root. One thing to keep in mind, make sure you're paying attention to the index symbol, because it's really easy to just look at this and think it's the square root of 16, when in reality you're looking at a cube root. Okay, so first off, we know that 16 is not a perfect cube. And remember, you can take cube roots of negative numbers. So what we're going to do with 16, I'm going to go ahead and show the work here. We're going to split negative 16 up into 2 perfect cubes. Well, the largest perfect cube to go into 16 evenly is 8, so we're going to go ahead and write down negative 8, and negative 8 needs to be multiplied by 2 to give you negative 16. And let's go ahead and use the index rule to simplify all our variables. So 3 goes into 3 evenly once, so that means we can simplify an a without any a's being left inside the cube root symbol. 3 goes into 4 evenly once, which means we can simplify a b, but that one remainder means we're going to have to write a b underneath the cube root symbol. And since this is c to the first power, 3 does not go into 1 evenly, which means we cannot simplify out any c variables, so we're going to rewrite c underneath the cube root. So let's go ahead and simplify this answer. We know that the cube root of negative 8 is negative 2. We're going to go ahead and write our a and our b since they're outside of the radical next. And anything that's underneath of a radical, instead of writing them as 3 separate cube roots, we can write one large cube root and put all those underneath together. So the 2, the b, and the c. Let me clean that up a little bit right there. And once again, I left a little bit of space so this doesn't look like b cubed. We know that the 3 is the index.